Okay, for number 11, we have a compound interest problem here. You have $5,000 to place in a CD, that's a certificate of deposit, it's a savings account, for 5 years. The CD pays 3.6% annual interest compounded continuously. How much will the CD be worth at the end of 5 years? So first off, we have two compound interest formulas. One is for interest compounded periodically, and one is for interest compounded continuously. So that's clearly the one we want to use here. It's the one with the natural logarithmic function in it. Next up, we need to fill in the values for the appropriate variables. So we have $5,000. So that is what we're starting with. So that goes in for P, our principal, our starting value. We want it to be in there for 5 years, so that's going to go in for time for T. And here is our interest rate, 3.6%. We do want to change that interest rate into decimal form, and we multiply it by T, which is 5, our time, and that's going to give us our ending balance, or how much our CD will be worth at the end of that 5 years. So this one, we don't have to solve for any variables. It's really just a calculator problem. So you do want to make sure you know how to put those. Oh, I didn't write that right. Look, back up. I lost my E. Don't lose your E. That's important. 5,000 times E to the 0.036 times T times time. That's what we want to put in. Otherwise, you would have gotten totally the wrong answer. So 5,000 times E, and it automatically pops me up in the exponent there. I want 0.036 times 5. We hit enter, and there is our answer. We typically, I don't know that this one gives rounding directions, but we typically do want to round to the nearest cent when we're talking about money. So that would be 2 decimal places. So this is $5,986. And 9 cents. We put 9 cents because we had 0.86, so that means we want to round up. So after 5 years, that's how much money we would have with our interest compounded continuously. Number 12, we have a logarithmic function, and we need to answer what is the domain, the range, and the asymptote for a logarithmic function. Well, based on the definition of logarithm, we should know that you cannot take the log of a negative number and you cannot take the log of 0. So anytime we have a logarithm, we always need to make sure that whatever is in the argument of the logarithm, whatever we're taking the log of, that has to be a positive number. So to find the domain, that's what we want to do. You don't need to worry about that -1 when we're finding the domain. We need to worry just about the argument of the logarithm, and it has to be positive. If we subtract 5 from both sides, that means x has to be greater than -5. There is our domain. If we wrote it in interval notation, it would be -5 to infinity. The range for a logarithmic function. This is something we should know from study logarithms. The range is all real numbers. Doesn't matter if it's been shifted or flipped or shrunk or compressed or expanded. It is all real numbers for the range. The asymptote, there is a vertical asymptote when we have logarithms, and it is also based on the argument. When you take that argument and set it equal to 0, that's how you find your vertical asymptote. So the logarithmic function, this one in particular, has a vertical asymptote at x equals -5. Number 13, we want to condense this logarithmic expression. So we are going to use our properties of logarithms to put these together into a single logarithmic expression. First thing we need to do, we cannot combine logarithms that have all these different numbers in the front. So we want to use the property first where we can take that number in front, the coefficient, and put it up into the exponent of our logarithm. So this first term would be written as log base 6 of x to the 6th. The coefficient goes up into the exponent plus log base 6 of y to the 1/5. Again, took the coefficient, moved it up to the exponent, minus log base 6 of z to the 5th. I did leave my sign there. You can take it. There's a couple different ways you can handle that one. So that is our first step. So now we can combine these logs because They are all log base 6. We couldn't combine them when they all had different numbers in front. So that's why we have to use that first property. Now, the sum of two logs is equivalent to the product of those logarithms. So since these are both log base 6, this is equivalent to x to the 6th times y to the 1/5 minus log base 6 of z to the 5th. So we combine those first two, the plus becomes multiply. When we combine them, we can only combine them when they have their matching bases. Now we can combine again. This time we have a subtraction, and our properties of logarithms show us that with that subtraction, that means we turn this into a division with z to the 5th in the denominator. So there is our condensed single logarithmic expression. In the answer key, it wrote this 1/5 as a radical. So equivalent answer, either one is good. You could also write this as the 5th root of y over z to the 5th. Those are equivalent answers. Number 14, now we're talking about solving with logarithms. So we have a couple of different things to try. Basically, when we have an equation that has some terms that are logarithms and some terms that are not, our plan of approach should be to get the logs on the same side and then combine them. So that's what I'm going to do first here. I'm going to take this logarithm and move it over to the other side of the equation by subtraction. So after I do that, what we have is the log of x plus 3 minus the log of x minus 2 equals 2. Moved the log to the other side. Now I can combine these two logarithms. They are both the common logarithm, or log base 10. Okay, when we don't have a little number down there, we should know that's log base 10. They are subtracted, so we can combine them through division. So it becomes a single log of x plus 3 over x minus 2. Once we have a single log on the left and a number on the right, we want to use the definition of a logarithm to rewrite this equation into its exponential form. Remembering again that when we don't have a number here, that is the equivalent of having a 10. So we take the base, that's the little 10. The answer of the logarithm is always your exponent, and we set that equal to our argument. Again, look up the definition of logarithm if you don't remember that. 10 squared is 100, so we can figure that out. Then we want to multiply both sides by x minus 2. When we do that, I will distribute that 100, so we have 100x minus 200. On the other side, we get canceling, and we just have the x plus 3. Let's gather up our like terms. So we'll take this x over here with these x's. I'm also going to add this 200 over with our other constant. So we end up with 100x minus x is 99x. Those cancel, and 3 plus 200 is 203. Divide by that 99. And I don't think that one reduces. There is our final answer. Now, there is one thing we should always check when we have a logarithmic equation. We want to make sure that this value for x doesn't give us a negative in our log argument. We don't have to do an exact calculation. 203 over 99, that's a positive number. A positive number plus 3 more, that's still definitely going to be positive. What about over here? If you're not sure, if you can't kind of reason that through in your head, just do it. Let's see. If we put in 203 over 99 for x, and we subtract 2, is that positive or negative? It's positive, so that one checks out okay too. So this is a good answer. This one very similar, okay? We have a mix of logs and terms that don't have logs. So just like the last one, it's even better because the logs are both on the same side of the equation already, so that's good. We can go ahead and combine these, again, using our properties of logarithms. When we have matching bases and they are added together, we combine them with multiplication. Once we have a single logarithm on the left, we then want to use the definition of logarithm, which is take the base 3, raise it to the answer, the exponent of 3, and set that equal to your argument. 3 to the third is 27. We can calculate that. Use your calculator if you're not sure. And we do need to go ahead and FOIL this out, multiply out on the other side. We get an x squared, we get a minus 2x, a plus 4x, and a minus 8. This is now a quadratic equation, so we need one side to be 0 before we can solve it. So we get 0 equals x squared. Combine those two like terms, that's a plus 2x. And negative 8 minus 27 is negative 35. So we can either factor or use the quadratic formula. I'm going to go ahead and factor here. 35 is 5 times 7. To get a positive 2, I would need a plus 7 and a minus 5. So I get two answers. Either x is equal to 5 or x is equal to negative 7. We need to check those answers because you cannot take the log of a negative number. If I put a 5 in here, 5 plus 4, that's positive, that's okay. 5 minus 2 is also positive. That one checks out okay. So that one's a good answer. Negative 7. If I put a negative 7 in here, negative 7 plus 4, that's negative 3. We already know this one doesn't check out. So that is not a solution. X equals 5 is our answer.